let's FOIL this out. We're so good at foiling now, it's ridiculous. This is the same thing as x squared minus 5x. Okay, negative 5 times x, or x times negative 5 is negative 5x. Cool, I'm okay with that. That's the outsides. Inside is 5x, so we'll add a 5x. And then we have a 5 times a negative 5, so negative 25. Let's combine like terms. And it's usually the linear term, so it's minus 5x plus 5x. That means there's no x's in the middle. Okay, so those cancel out. X squared minus 25. That's kind of weird. Normally when we do these, we have a linear term left over. Here we have a case in which the linear term goes away. Furthermore, you can see that both of these terms are perfect squares. We have x squared, and then 25 is a perfect square of 5. That's not a coincidence. This kind of works in general. If I have plus something else, and I have that same binomial, but just its conjugate. The conjugate is those same two terms, but you do the opposite operation in the middle. So the conjugate of a plus b would be a minus b. You're going to see conjugate a couple more times, so it's good to know the definition of that word. And then similarly, if I started with a minus b, the conjugate of a minus b would be a plus b. So it doesn't matter which one you start with. If you have two binomials and they're conjugates of each other, the shortcut is you have that first a, you have the first thing in both of them, you square that. Then forget about the linear term. We've shown here that they're going to cancel out. So you just have a minus, and then whatever that last thing is, squared. This is the shortcut, and this is what you'll come to know and learn and love, is called the difference of squares. It's really important to understand when something is a difference of squares. So, for instance, if I just gave you right away x squared minus 49, I immediately know that it came from x plus 7, x minus 7. If I had 4x squared minus 121 y to the 6th, is that a difference of squares? Well, it's not really in like this form where we can clearly see what the square root of it is. But let's try to pick apart if these are perfect squares. Well, what squared could equal this? Well, not 4x squared like this, because then this would be 16x squared. 2x squared like this works. And then same thing with 121 y to the 6th. That's a little complicated, and you're not supposed to know this yet. If I were to show you that it is 11y cubed squared, yeah, that makes sense. We hit each of the different bases by that exponent, which is going to be, I will long ways this out so you can see it like that. And then 11 squared is 121. Y cubed squared is y to the 3 times 2, which is y to the 6th. We've identified what our A and B are with the general form of this. This is going to be 2a plus 11y cubed times 2a minus 11y cubed. Again, I don't know how complicated these are going to look right now because you're not supposed to know how to break up this y to the 6th without heavily learning roots. For me, math just kind of blurs together and it's just so circular. Not circular logic, but it's really cumulative. It kind of wraps around itself. Something like this is, I'm not sure when you're supposed to learn it, whether it's algebra, algebra 2, pre-calculus even. Sometimes it's a little hazy for me. That's why I make myself some notes. But the point is, here's another one. X squared minus 1. Is that a difference of squares? It's called a difference of squares because you're literally subtracting, which means difference of two squared things. Difference of squares. Yeah, that is. 1 is a perfect square of 1. So we have x plus 1, x minus 1. Great.